In this video, we're going to do some conformational analysis of different substituted cyclohexane rings, and then we're going to compare the data that this software gives us to actual data from a table in our book. So let's go ahead here and, like we did in our previous video, and open up our DS Viewer Pro by clicking this icon right here. And this is what you'll do in your computer lab. It brings up this prompt to which we just respond by clicking the OK. Now we're here at our blank canvas. What we want to do is begin by laying down a cyclohexane ring. That's super easy. If you click this ring tool right here and then click right here in the canvas, it'll automatically throw down a cyclohexane ring. We can see the hydrogens in this cyclohexane pretty easily by clicking this H tool right here. So click that, you can see the hydrogens. Now if we click the rotation tool over here to the left, you can rotate that around and see where those hydrogens are. Let's make it a little bit bigger and centered in our screen by clicking this black box up here. Now, once again, we're going to rotate this thing around. You can see that the hydrogens, as we stared right down the plane of this cyclohexane ring, are obviously not in the correct shape or conformation that they would be if this cyclohexane were in the traditional chair shape or conformation that we're used to learning about in organic chemistry. Obviously, it's not, and the reason is because it has not yet been energy minimized. That is, the software hasn't adjusted this to the most stable shape that this molecule possibly can arrive at. So what we're going to do is do that by clicking Modify, Drying Minimize. The parameters that we'll choose is going to be 1,000 iterations, 0.01 convergence criterion. We check all three of these boxes, and then we'll choose one step right here in this blank. We now hit OK, and the software will begin moving around all of the bonds in an attempt to find the lowest energy that it can. Upon doing that, you can see that it looks a lot more like a chair. That might not be obvious, but with the rotation tool selected, we can rotate around and look at it, and yeah, it kind of does. Now, I'm going to rotate it around a little bit more so that we can kind of look at it in a plane. It's a little bit tricky sometimes and frustrating. Yes, if you look at that, you can see that it looks a lot more like the sort of slanty bow tie that we'd expect to see in a chair. And that's even clearer if we make these hydrogens or remove these hydrogens by clicking this hydrogen removal tool. And it doesn't, they're still there, they just aren't visible. You can see once again that's a beautiful slanted bow tie. Which is a gorgeous chair, just like we learn in organic chemistry. So that is a nice energy minimized cyclohexane ring. What we'll do now is change this molecule from cyclohexane to methylcyclohexane. We'll begin by clicking this H box so that we can see all of the hydrogens. We want once again to replace one of these methyls with a carbon. So we click this selection tool here and then choose one of these hydrogens. I'll go ahead and type the letter C on my keyboard, and it will change it now to carbon. So this is methylcyclohexane. If we click the rotation tool, we can see it a little bit better. And we can see it even more clearly if we remove the hydrogens by clicking the Hide Hydrogens tool right here. As you can see, the methyl group is in an equatorial position. What we'd like to do is calculate the energy level of this equatorial methylcyclohexane. We'll go up here to Modify, Drying Minimize with these parameters, and then hit OK. It will now rearrange until it finds a local energy minimum. To see what that energy level is, we go up to Window, New Data Table. The final drying energy of an equatorial conformation of methylcyclohexane is this number right here, 13.72 kilocalories. Go ahead and write that number down now. Let's go ahead and X this window to return us to our canvas. I'd like to go back to our cyclohexane ring by clicking the Select tool, clicking this atom, turning it back into a hydrogen, and then clicking this button to show all of our hydrogens. I want to get this back to the minimized cyclohexane conformation that we were at before, so we'll click Modify, Drying Minimize, and then take it all the way through. Now we should be back at the energy minimized cyclohexane conformation. I now want to change one of my axial hydrogens to a methyl group so that we can get the energy level of the axial conformation of methylcyclohexane. Go ahead and click the Select tool right here, select an axial hydrogen, and type the letter C on your keyboard to convert it to a methyl group. Now to get the energy level of this molecule where we have an axial methyl, let's go up to Modify, Drying Minimize, and then with these parameters chosen, we'll hit OK. You'll notice after it's all finished that the methyl group up here is a little bit puckered. That is, it's not exactly straight up the way we typically draw it for an axial methyl. The reason, of course, is because this methyl group is much closer to these hydrogens because it's in axial position, which kind of forces it to want to push away from them and be not straight up and down, as a hydrogen would be. To get the energy level of this conformation, we go to Window, New Data Table. The final energy of this conformation is right here, 15.01 kilocalories. Go ahead and write that down. With that written down, let's X this window, and now we'll change this to an isopropyl group. Remember, an isopropyl group is a group that has a methyl with 2 of the hydrogens being replaced by methyl groups. So we want to change 2 of these hydrogens into methyls. It's interesting because as we rotate around, we could change this hydrogen right here to a methyl. This hydrogen's pointing kind of toward the interior of the ring, but probably it's going to be more favorable to have these 2 be methyls and this one pointing toward the interior being a hydrogen as opposed to the other way around. So we'll go ahead and select one of these and type the letter C on your keyboard to convert it to a methyl, and then the other and convert it to a methyl as well. You grab the rotation tool and rotate back up. You can see that we've got a nice isopropyl group that's a little bit clearer when we remove the hydrogens from view in an axial position. Let's go ahead and go to Modify, Drying Minimize, and select OK. To see the final energy level, we'll go to Window, New Data Table. The final drying energy of this axial isopropyl conformation is 24.34 kilocalories, which you should write down right now. Go ahead and X this window, and then, as I outlined before, reconvert this molecule back into your parent cyclohexane ring. Now that we're back at our parent cyclohexane ring, what we're going to do is replace one of the equatorial hydrogens with an isopropyl group and then get an energy level for that molecule. Go ahead and grab your selection tool, click on one of the equatorial hydrogens, and type the letter C to convert it to a carbon. Now you'll grab 2 of these hydrogens and convert them also to carbons by clicking on each one and then typing the letter C. This is now a nice isopropyl group dangling off of the equatorial position in this cyclohexane ring. You can see it a little bit easier if you remove the hydrogens again. There, it's pretty clear. Let's go ahead and get the energy level of this by clicking Modify, Drying Minimize, and then hit OK. To get the energy level, I'd like to click Window, New Data Table. The energy level of this molecule, which has the isopropyl group in the equatorial position, is a little bit less than the axial one that we just got at 22.69 kcals. Go ahead and write that down. For right now, what I'd like to do is assign you to do the same process for a Tertbutyl group. That is, a carbon with 3 methyls coming off of it, getting a separate energy level for both the axial and the equatorial conformations. I will let you do that on your own.